Hello everyone. This is another way to solve the simulation, a more professional one, because basically you use a circuit analysis program. There are many available. Multisim, you already know about it. This is PSpice. I prefer to use it for many reasons. Two of them is, one, it is free. You can just download it, the light version, and it mainly consists of everything. Everything is there already, and also it is more. It gives you more options to reach a more accurate solution. Multisim, on the other hand, like here we found one problem. You can change the value of k. You can change the ratio between the length and the width, but I found out that the answers that the result of the simulation is not accurate. Anyway, so we start a new project. We name it whatever we want. Okay, then I think there will be a pop-up window. You just choose blank project, and this is what will appear. So if you're using the program for the first time, you have to add the library of the parts. You just press here, and then you do select all. So Control A, something like this. Yeah, everything will be collected, and then just open, because you have to add the libraries for the first time. Basically, the libraries consist of every single part. I mean, the part itself, when you buy it, you can just simulate. I mean, for the most famous ones. You don't need this window. You can just use this one, which we will do. We'll start by just adding the parts for the circuit as it is. So start by adding resistors. The symbol for resistors is R, so just press R and enter, and then we can place the part whatever you want, but we don't want it in this orientation. We can just rotate it by pressing R, and then we just put here, and there. Okay, another part that we need is the VDC, which is a voltage DC source, because we need to supply voltage, VDD basically. So since the VDD is positive, we need to change the positive terminal to be this way, or you can just put it parallel right here and then just connect it. Just mind the polarity while you do it, and then we connect the most important part of all actually is the MOSFET itself. So here I'm going to use for the MOSFET itself, there is many actually according to the manufacturer and so on, but here I'm going to use the ideal one, because there is nothing that actually has this there is no real part that has this kind of K from what I've seen. So you can just use the ideal one, which is, the code for it is M-break-N3. This is an enhancement N-type MOSFET, and then you can just press enter. Here it is. Just put it here. Just like we did this, and then also we need the ground. It is common, but for the sake of simplicity, I'll just put 2. So here 1, another one is here. You can just connect. So to connect, you have to use the wire. You can just press W, or you can press right here. Just connecting. Make sure you don't go over something. This type of arrow up here, which warns you that you are short-circuiting the part itself. Alright, here we go. Alright, so now we change the values according to the ones we have. This one is 12 volt supply, and this one is 1.2K. This one is 1 mega. Make sure the M is capital or uppercase. So this one is 0.5 0.51. Okay, so 0.51. Okay, all right, now the parameters we want to choose to change is the K and the threshold voltage. So since we're not using a certain part with its own parameters, we're using the ideal one, we have to edit these parameters. So we right click and then choose edit PSpice model. Okay, a window like this one will appear right here. Okay, and you will find basically only this part exists. Only this part exists. Okay, this is the ideal case. So we add these values. VTO is the voltage, is the threshold voltage. KP, W, and L are all variables that relate to K. This one right here. You can see that from the formula itself, PSpice multiplied the whole thing by 0.5. There is a certain constant. So basically, the original formula for Kn is UN COX multiplied by W over L, which is width over length. But PSpice considered in this manner. So basically 0.5 multiplied by Kp is the same thing for this one. And they are basically just a constant. So the thing that actually manipulates the value of K is the ratio between W and L. Okay, so you put this one as just 1x. Okay, just put it as x, and then you put here the value that you want. Let's say here it's 0.56, and then you just solve for x. I got a simple fraction, which I actually used as the fraction the ratio between W and L, which is right here. So 112 over 5. They are all in micromilliampere, I think. Micrometer. Anyways, so using these parameters, we have our lovely MOSFET. So just yes. Anyways, so this is what we have here. The MOSFET here has the same parameters and everything. So let's just do a test. Actually, this one is not the one that will help us to draw the IV characteristic ADC. This one is just for verification. So just let us do some kind of simulation first. So you can just type new simulation. You can just put some name, and then something like this will actually appear. Okay, something like this. So I want to change the analysis type into bias point, which means that everything is in DC. Okay, and I just want to get the values of the voltage, the currents, and the power at different nodes. So this is what we actually have here. Let me just remove this. Okay, so and then you can just run the analysis. Type. Okay, there is nothing that you will actually need to edit or anything. Just bias point and then run. You can show the voltages along the nodes. You have the current and then the work. Power at different nodes. You can also use another type of analysis, which is transient analysis. It is like it changes according to time. As long as we are in DC, so there is nothing that will change, but it will help us to use some kind of a voltmeter, which will enable us to calculate the value of VGS here. You can just place it right here, just like for confirmation later on. This one has to be the VGSQ. Okay. So we run the analysis and we have it here. By the way, this one will, this one is not, as you can see, we can't just detect it. So we can just, decide whether it's 6 point what. So later on I'll be using this value right here. So some values here appear according to the x-axis and the y-axis. Y-axis will be for voltage in this part, and the x-axis will be for microseconds. So as you can see here, VGSQ is equivalent to 6.41 as it appeared here. So let's start by doing the curve first. So how are we going to make the curve? First of all, I'm closing this one. So to draw the curve, you don't need all these resistors and so on. Okay, you just need to know, considering this MOSFET only, okay, with a certain voltage source and VGS. As VGS changes, how will ID change? Because this is actually the IV characteristic. It's between the voltage of GS and the current of ID. So you can do that by actually starting by opening a new page, or you don't need to make a new project, or you can just remove this one. So all I did is new page. New page, it means it's still under the same schematic, which means you still have the same analysis you already created, okay, and it's still under the same project, which means the same parameters for this one, for the parts you edited already. So, and I need you to create the circuit. So we put the same value, we put the same part here, the same MOSFET that we already used, and make sure that its parameters are the same as the ones that we did, and you put VDS as 12 and VGS as 0. See, here it's the same. VDS is 12 because it's just constant. Actually, it will not affect our analysis by any means. And VGS. Why did I call this VDS? Because it's actually parallel to VDS here, and VDS is also parallel to VGS here. Okay, so what we need now is a type of analysis called DC sweep. I got one already here, so I'm going to show you. So you put new analysis, you choose new analysis, you call it whatever you want, and then when it opens, this window appears. You choose the analysis type as DC sweep, okay, and basically it is an analysis that allows you to change the value of one part, okay, and make you know, like a gradient of the values of this part, which will allow you to see how this part affects the values you want. For example, here we're looking for ID, how ID is affected by VGS. Okay, so I'm going to do only one sweep. So you can do this kind of sweep according to two variables, not only one, and this will actually show you the multi-line graph that we see in the lecture notes. So here we want to only do the primary sweep for VGS. We choose the voltage source, and you need to give the same name as this one, okay, because you have to select the type of it, VGS, and it's just linear sweep, you know, like it increases 0, 1, 2, 3, 4, and so on. It's not logarithmic. It's not about E. So for the start value, you start from 0 until 15 volts, which is very good for our analysis, because we already, from the paperwork, we can already know that when VGS is equal to 12, ID is already 0, and this is the end of our load line. Anyways, so the increment, you can just put whatever you want, but the more resolution you give, the more accurate your graph will be. And then we put OK, and then you run. I just need okay. So, and then you just, you know, like make sure you're choosing this analysis. You press run. Okay. So the analysis run. But what is this? Okay, so the data is analyzed, but you need to know, but the program needs to know which thing you want to track. So which parameter you want to track. So you add a trace. We want to track ID, right? So we don't need the power, we don't need the obvious things, we need the voltage. This one, we're going to choose this one. Make sure that this is actually a trace expression. You can just not only add one parameter, you can add it to another one, and you can do mathematical calculations and functions of this expression, or in this type of parameter you're going to pick from here. We just want to show ID, how it changes with VDS, which is right here, as you can see. So we press OK, and here we go. This is our lovely graph. Finally, something that we can understand. It's just a graph there, but you can see that the slope is very low. You expected it to be more steep, according to the graphs you got. It's just a matter of resolution. Actually, here it starts 20, 40, 60, and the graphs we just draw, like it ends with 10. You can just change that by zooming and so on. So I can just pick this one. I want to zoom from 20. Let's say I want to zoom from 10 to 12. And actually, we might be able to know why we have to do that, because we already know that the load line, so which is our next step, we need to draw the load line from 12 to 7.02. We already gone through that. When ID is 0, VGS is 12. When VGS is 0, ID is 7.02. So how to draw the load line? You can just like put some kind of label. You have to draw it by yourself. So we just pick from here, from plot. You choose label, and we want to make a line. Okay. So this line, as you can see here, actually you can use these values to detect your accuracy. Like I want here to be 12. Yes, it's already there, but I want Y to be 0. So just I'll just plot label again line. So I want it to be from here. Oh, yeah, by the way, one hint, don't pull, just click. Okay, so we have this one here at Y equals 0, and we want it to be 7.02. This might seem as a hard mission. Sadly it is. So this one, as you can see here, 0.00638. Need to go up. Okay, here we go. 7.02, which means actually it's kind of here. All right. So here's our load line. We want to know the IDQ and the VGSQ. How can we know that? It's actually simple. You just put the cursor over this point. You can even zoom more, like this. Okay, so the cursor is here, and then you can see the values from here. So it's right here. So you can all see that the VGS is 6.42. VGSQ, and the IDQ is 3.28 milliampere. Actually, we can actually see that this is accurate, because the voltage VGSQ being 6.42 is what actually we got here in the first simulation we did, and the transient, whatever. Yes, when we got this one as 6.42. Yes, right here. And for the DC, for the DC bias, when we ran this kind of thing, we can find that the current here is 3.266 for ID, which is actually very near to the value we got. That's it, actually. That's pretty much it. I'm sorry for talking too much. It's been a very long video. I hope it helps you in the future. I just, like, it took me too much time just because I was explaining the program itself. Hope you use it. Like, you can use this program to check for the values of the unknown, to check for the values of the unknown values you got and the circuit. Like when you're solving the question and you want to verify the answer, you can use such programs. It will help you much. Hope this one also was useful. Thank you.